Alrighty, good morning, everybody. Let's get some participation up on the whiteboard. Again, just give your best shot. I know with yesterday and everything that happened, we didn't really kind of go over this, but just kind of do your best. Hopefully you watch the recording so you have some kind of background on it. But just do your best as I get the last few people for attendance here. Excellent. I'm seeing some people popping up there. Nice job. I see Evie up there. I see Hunter up there. Good, nice job there. You too. Excellent. All right, so let's go ahead and go over this because I want to make sure we have plenty of time today in class. So I'm going to go ahead and put your whiteboard tools on hold. And again, if you have the opportunity, make sure you watch that recording just so that you have some background knowledge of it. We are going to be talking about some phase changes today, but not as much as in depth as we did yesterday. So watch that recording. I will put it up on our content section. Again, I will tell you yesterday when we were had our major system meltdown, you have been excused from notes from yesterday and you were excused from participation. So do not worry about that. No, you were excused from all the whole notes and you were excused from participation, everything. So don't worry about that. If you look on your gradebook, you will see that you were exempt from your from our one E notes, okay? So our 1E notes you were exempt from, okay? But I do want to have you make sure you watch the recording. I will put it back. I'll put it up on. It's an old recording, so it is an older recording, but it still has the same information. So just make sure that you watch that, okay? All right, so let's go ahead and take a look here. So when the sun dries the sidewalk after a rainstorm, that is what? So think about it. If we had a puddle of water, and we see this all the time, especially yesterday, we had some rain yesterday, and all of a sudden, maybe in the afternoon, the sun came out or just stopped raining, and eventually what happened was that all of a sudden your puddle went bye-bye. So what happened there is what we call vaporization. Okay, and so that is a phase change, and vaporization is when this water is being evaporated back up into the atmosphere. Okay, the next part here is a little different. Now we're talking about endothermic and exothermic processes, and especially when this is important because we're going to talk about it today, especially when we talk about chemical reactions in this class. It's important to know endothermic and exothermic reactions, whether heat enters into the reaction or whether heat exits that reaction. So if thermal energy is absorbed, so we're talking about heat energy is being absorbed, causing temperature to increase and particles to move faster, that is what we call endothermic process, and that is where heat enters, and where our key word is here is going to be energy is absorbed. Okay, energy is absorbed. So whether think about it, we are doing jumping jacks, and as we're doing jumping jacks, heat is entering. We're heating up our body, we're increasing our temperature, heat is going to enter into our body, and so then our particles will move faster. Just kind of think of it like that to kind of give it your take on it. We'll talk about exothermic a little bit later. So let's go ahead and jump into this. I'm going to give you your notes here. So when you get your notes, please go ahead and start opening up your notes and raising your hand as I go through announcements today. Remember, Class Connect sessions are recorded and distributed for learning purposes. Please do not put any personal information or information of others into the chat box for your protection and the protection of others. Make sure that you are school appropriate and respectful in the chat box at all times, and always participate. I know this is not an issue here in third period, so nice job, everybody. Just keep up the good work here. Today is day 8 of our 60-day adventure. I cannot believe it. It is December 8th, and so we're going to talk about matter and energy and do our 1F notes. Okay, so let's go ahead, and before we do that, I want to do an announcement. Remember, our Chemistry Unit 1 project is due tomorrow. So it is going to be worth a 55% of your grade. That means it's going to be worth the whole entire 55%. Because we only have one project in, it's going to be a big chunk of your grade. Now, how do I grade this project? Well, I grade it as a benefit to you. I grade it on our 5 to 10 scale as long as you provide a valid attempt. So if you give me a valid attempt, you are going to get at least half the points, okay? So I'm not going to give you a 0. I'm going to give you half the points if you give me a good, solid, valid attempt. And it may be wrong, but that's okay. I give you half the points. What do I mean by a valid attempt? Well, I don't want to see any blanks. I don't want to see any random answers. It should be clear that you watched the recordings and that you went through every step. I don't want to see a valid attempt. Please don't do this. Yeah, no worries, RMS. One thing that I see very often is because you don't want to have it overdue or you don't want to see it anymore in your overdues or anything else, you just turn in a blank project. Folks, that's a waste of my time and it's a waste of your time. Please don't just give me a blank project. I will just shoot it right back to you, okay? So look for do a valid attempt. We give you all the resources. We give you the recordings so that we can you could be successful. Use it. Remember, use it. And if you have any questions, please, by all means, let me know. Yeah, no worries, Alyssa, no worries. Now, this is technically due Thursday, December 9th at 4 p.m., but I will not be zeroing out your grades until next week. So just kind of be aware of that. I will not be zeroing out those grades. Now, really, to be real technical, this project really isn't due until March 7th. That's the end of the trimester. Do I suggest that you wait till the end of the trimester? Absolutely not. Okay, I see it every trimester is that students try to, scramble to get their grade passing and scramble to get it done, and it's just not worth it. Don't do that to yourself. You're going to stress yourself out, get overwhelmed. Don't do that to yourself. Now, if you're a couple of days late, yeah, not a big deal. Okay, we do start a new project for Unit 2, but again, not a big deal if you're late, okay? I don't dock you for being late. I don't take away points for you being late. It's just I want you to make sure that you know your time frames, okay? So you don't get overwhelmed and you don't get overpacked, okay? Yeah, Alyssa, we could definitely get together and work on that. Okay, so today we're going to be working on matter and energy. Like we said, we're still working with structure and properties of matter. Food project is on schedule for due tomorrow. But today what we're really going to be talking about is define and apply conservation of matter and energy. We're going to define thermal energy, heat of fusion, and heat of vaporization. We'll explain how thermal energy affects the particles when matter is in a single state versus when it undergoes what we call a phase change. And then we're going to identify and define exothermic and endothermic processes, okay? So with that being said, everybody should have their notes open with, and with the hand raise, I will go ahead and put our notes again into the chat box. Make sure you open those up for those of you who are my late birds or just haven't done it yet. I'm going to give you all 20 seconds up on the clock. Make sure you get it in. If you are watching the recording, click Grades tab, scroll down to 1F Notes, and start your quiz. For everybody else, go ahead and raise your hand up here in class. So still looking for a few people, 5 seconds. Make sure you click on. So looking for Alan, RMS, let me know how you're doing, my friend, in the chat box. Good, awesome, thank you, RMS. So Jens, Colin, Jacob, JJ, and Mario, raise your hand. Thanks, Isaac, I saw you popping up. Hunter, thank you, JJ, awesome. So Alan, Jens, Colin, Jacob, JJ, and Mario, get your hands up. Remember, just go ahead and just keep your hands up. Thanks, JJ. I saw you popping up there. Perfect. Just keep your hand up. Mario, Jacob, Colin, Jens, and Alan. Please raise your hand. Last few people. Last few people. Again, to get that participation. Thanks, Brian, or Jens, I'm sorry. Awesome. Alan. Perfect, Alan. Thank you. Colin, Jacob, and Mario. Colin, Jacob, and Mario. Last three. Last three. Let's get 100% with our participation today. All right, let's go ahead and move on. Thank you for those who are participating and actively taking charge in class. So let's talk about conservation of matter and energy. When we hear the word conservation, I always think of recycle. What is some words that you think of when you hear the word conservation? What do you think of when you hear the word conservation? I think of recycling. What are some other words you hear? Okay, you heard conversation. All right, I like that. Conserve the water. So keep the water. Yeah, I like that one, Isaac. That one's a good one. Yep, absolutely. Yeah, I agree with every one of you. Now, when we talk about it in science, we're talking about matter and energy. So matter and energy do not mysteriously appear and disappear. It's not a magic act in the universe. There is energy, and energy stays where it's at. Conservation of matter and energy is when matter changes form. There is no increase or decrease in the amount of energy. Energy is neither created nor destroyed, but energy is either transferred or converted to a different form or transferred to a different location. So again, it doesn't miraculously appear and disappear. It actually is just being transferred or converted into a different form. Okay? So let's take a look at this. Now, before we take a look at these graphics, I do want to take a look at the total quantity of matter and energy in the universe is fixed. So whatever energy your matter has, it's not going to get any bigger or any smaller, but it can transfer. And we'll talk about that when we talk about potential and kinetic energy. We've talked about that a little bit in physics, so you should have a good idea on it. Bring that forth. Well, let's take a look here. So if energy can be transferred to a different location, we can take a look at this chemical reaction. I have two hydrogens on this side plus an oxygen on this side. When I combine these two gases, energy is being created, and what it is creating, it's creating a new substance which we call water or liquid, H2O. Now, on their own, they are both gases, but when we create them, or when we combine them in a chemical reaction, which energy is being transferred, we then are transferring that energy to a bond in which we create a new substance like a liquid water, H2O. Another example is here when we look down at this light bulb. Obviously, we have electric energy coming into the light bulb, whether it be from a plug or what have you, but we have electric energy coming into the light bulb. Again, if there is going to be the same amount of electric energy coming in, and then obviously it's going to be transferred into different forms of energy, either into a light energy or into a heat energy. So when we put our hand next to a light bulb, you're going to feel the heat, and then obviously you're going to see the light. So again, those energy forms are just being transferred. Total amount of matter, or total amount of matter and energy, is fixed. It's just being transferred into a different form. Okay, it's just being transferred into a different form. Isaac, most energy, yes, does get transferred into and eventually end up as a thermal or some kind of heat energy. Yeah, I would, and then dissipate. Yeah, absolutely. But it doesn't necessarily disappear. It doesn't really necessarily disappear. That heat energy has been then being absorbed back into the atmosphere, or back into being in a gas. Okay, in the gases around us. Okay. Yep, absolutely. Good, Isaac. Great. All right, so let's go ahead and lock in number 2. A lot of you have already locked in number 2, so I'm going to go ahead and just give you 25 seconds to go ahead and finish that up. So go. Raise your hand when you're finished. All righty, so still looking for Alan, Aramis. Let me know how you're doing in the chat box. Colin, David, let me know how you're doing in the chat box. Hunter and Jacob. Colin, and Jacob and Colin. Awesome. Thank you, Alan. Beautiful. So David, just let me know how you're doing in the chat box. RMS, go ahead and raise your hand. Perfect. Awesome. Thank you so much, Colin and Jacob. Colin and Jacob. Perfect. Nice job, everybody. Nice. Let's go ahead and move on. Beautiful. Love the hustle. So let's go ahead and take a look at this. Conservation of matter and energy says that energy cannot be either created nor destroyed. Now, if you remember back in physics, we talked about the unit of energy, and that is joules, right? We know that the unit of energy is joules with a capital J. Now, hopefully you also remember potential and kinetic energy. Remember, potential energy is that stored energy an object has due to its height. So looking at my skier up here, this is going to be a 100% potential energy, because obviously it's stored energy. They are at rest. They are at so stored energy, and they are at the highest point within this hill or jump. Okay. Now, when you look at the kinetic energy, remember kinetic energy, anytime energy an object has due to its motion, that's when if this skier starts to move, it then has kinetic energy. Now, what's important here is I want you to take a look. How much potential energy does this skier have? How much potential energy does this skier have? Look right here. Who can tell me in the chat box? How much potential energy does the skier have? Yeah, good, Emily. Yes. Good, Isaac. I see you in the chat box. Good. Let's get some more answers up. I want everybody participating. It makes class a lot more fun. Good, Evie. Excellent. Yeah. Perfect. We notice that the potential energy is 50,000 joules, right? We don't have any kinetic energy because that skier is at rest. It's not, they are not moving. But once that skier starts to move, we are transferring from potential energy to kinetic energy, right? Because the skier is now moving. So now energy is being transferred to kinetic energy. How much total, if you add these two numbers up, 20 plus or 2 plus 3, what do I get? How much total energy do I have? Good, Hunter. Yeah, I have exactly 50,000 joules, right? No energy. If I come back to here when I look at conservation of energy, the total quantity of matter and energy is fixed. That means it is 50,000 joules. Nothing has changed. Nothing was created. No energy was destroyed, right? It was just being transferred. It was being transferred from potential energy to kinetic energy. And so as I move down my hill here, I will notice that if I add these numbers up, I'm still going to get the total amount of energy as I did when I started, or the total amount of energy as when I ended. So if you look here at the very bottom of the hill, when the skier is going at its fastest point, okay, at the bottom of the hill, the fastest point, and my total kinetic energy is 50,000 joules, it matches my total potential energy up here, right? Again, it just transferred. It does not change. Nothing is created. Nothing is destroyed. It is just transferred from potential to kinetic energy as we move through this hill. So how much total energy does a skier have at every point? Who can tell me in the chat box? How much total energy does that skier have at every point? Good. Yep. Excellent, Isaac. Excellent, Emily. I agree. It is going to be 50,000 joules. Now, I'm going to go ahead and take a look here. I'm going to screen share with you really fast how to do this. Again, if you forgot how to do this. Let me grab my screen share. All right. So if you scroll down, oh, that was craziness. If you scroll down to number 3, if you go down here to number 3, you're going to see the answers box and the units box. In the answers box, you are going to go ahead. Yep, Hunter, it is a capital J. You're going to go ahead and put 50,000. You do not have to put the comma. You can just put 50,000. Make sure you got the right, correct number of zeros there. And then my unit is going to be a capital J for 50,000 joules. Okay, I'll go ahead and give everybody about 25 seconds to go ahead and get that locked in. Again, I have your answer right here, just like you should have it in your quiz. So 25 seconds, raise your hand when you're finished. Go, go, go. Ten more seconds. Nice job. Thanks, Evie and Vali, Rosalind, Isaac, Sybil. Good morning, Sybil. I don't think I said good morning. Marcos and Mario, good morning, my friends. All right. Let's go ahead and good morning. So Alan, Yins, Colin, David, Jacob, and JJ, go ahead, raise your hand up there. Good morning, Joey. I don't think I said good morning to you. And Hunter, good morning, my friend. So Alan, RMS, I know you're in the chat box, so you're good. Colin, David, let me know how you're doing in the chat box. And Jacob, thanks, JJ. I saw you popping up. Jens, thank you so much. All right. You guys are awesome. Love it. I love when everybody just participates. It's great. All right, let's rock and roll. All right, now we're going to do a complete on your own here. So complete on your own. I want to help you out with this one. So which of these statements about the conservation of matter and energy is false? I'm going to kind of flip back and forth as I read these statements so you have a good understanding of it. So looking at A, energy and matter cannot be created nor destroyed. That would be what? Looking right here, is energy is neither created or destroyed. So that would be true, right? What about number B? The total quantity of energy and matter in the universe can change. If I go back here and I want everybody to kind of look at their eyes and over here, can matter and energy in the universe change? Think about it. All right, so number C, energy can be converted to different forms. If I just even go back into here, I have potential and kinetic energy. Both of them are two different forms. Potential energy is at rest, while kinetic energy, we're talking about motion. Well, if I look here, energy is being transferred to a different form, from motion to, from rest to motion. Okay, from rest to motion. So think about it. And then matter can undergo reactions to form a different substance. If I come back to my water here, matter can go through a reaction to form a different substance. I have two gases, a hydrogen gas, oxygen gas. When I do a chemical reaction, obviously I form a different substance, which is a liquid, which we have liquid water. So think about it. I'm going to give everybody 30 seconds. Which one of these statements is false? I'm looking for the false statement. If you want to check your answer, please check your answer with me in the question and answers box. Again, I'm going to give everybody about 45 seconds. Go, go, go. Raise your hand when you are finished. All right, so just kind of wanted to take a look here. Remember, energy and matter cannot be created or destroyed, right? Nothing can be mysteriously come about. It cannot be created nor can it be destroyed. I can't miraculously energy disappear, okay? The total quantity of energy and matter in the universe can change. Well, if you think about it, no, it can't. Total energy, does the skier have at every point? It's always going to be the same, right? The only difference is that it's going to transfer, that is true. So think about it. Energy can be converted to different forms. Absolutely. From kinetic to potential energy. Absolutely. From electricity to light to heat energy. That's, those are different forms. Matter can undergo reactions to form a different substance. Absolutely. Looking at two hydrogen plus an oxygen, if I combine those in a chemical reaction, I get a new substance called H2O, which obviously is going to be a liquid, where I'm going to have two gases now form a liquid. That's a different substance. So that would be true. So think about it here. All right, so let me check in with a couple of people. Roz, Mario, Jacob, thank you. Good, Hunter. Yep, that's correct. So Alan, Aramis, let me know how you're doing. Colin, David, let me know how you're doing. Look at all these people popping up there. Mario, Jacob, Colin, and Alan. Good morning, Joey. Good morning to you, my friends. All right. All right, let's go ahead and move on. Nice job, everybody. High five to you. All right, so now we're going to kind of switch gears here. We talked about the conservation of matter and energy. Now we're going to switch gears to more of temperature, okay? So in our brainstorm, why does food need to be cooked to a certain temperature? Those of you who like to cook, let me know. Why do you think food needs to be cooked to a certain temperature? I'm not a cook whatsoever. I'm horrible at it, but I tried to give it my whirl. I mean, probably my best one is macaroni and cheese, but so it won't be raw. Good, Hunter. Yeah. Excellent. So it's safer to eat. Alyssa, I agree with you on that one. I do not want any undercooked food. If you've ever had food poisoning, it is the worst feeling ever, and I have. It's awful. I do not like it. That it's safe to eat. It won't be raw. What else? What are some other reasons why we want our food to a certain temperature? What about it just tastes better? Would you medium rare chicken? Yeah, nasty. Yeah, exactly. It just would taste better. I mean, some people like their hamburgers or their steaks a little on the rare side, but I mean, but people, if we actually cook it, it tastes a little better, right? We don't want raw chicken. First of all, you'll get super sick. Yeah. Yep. Yeah. You want it again, it tastes a little better. You don't want that rubbery. I have this thing with chicken. I can't have it rubbery. I like dry chicken. Some people are like, "That's crazy, Mrs. Sepulveda." I like dry chicken. Like I don't like it any moisture in my chicken whatsoever. So my husband, he cooks my chicken over off to the side and like overcooks it. It's crazy, but that's just how I am. It tastes better to me. Okay? So yeah, absolutely. Now, let's flip gears here a little bit. What instrument do we use to measure that temperature of food so that we know it's safe, that we know it's not raw? What is that instrument we use? What is that instrument we use? Good. Yeah, Evie. Awesome. Yeah, we use food thermometers. Now, I have a couple of food thermometers. I have this electric one right here. Again, pretty fancy dancy one. And let me tell you straight up, these are not my food thermometers. I have like I don't want to say an old-fashioned one, but this is just a more analog one where you kind of have to actually look at the numbers and to figure it out. And then I have another digital one, my Weber. And my Weber one right here. So again, easy way to take a look at our food to make sure it's cooked, to a safe amount so that we don't get sick. Yeah, exactly. My mom has that one, not digital. Yeah, a lot of people have these ones. Yeah, exactly. A lot of people, I mean, I have all three of them. I don't know which one works the best because I don't use them. But yeah, exactly. If you look in your kitchen, you'll probably find most of them will look like this one, right? So these food thermometers are what kind of, make sure our food is safe and that we don't have bacteria because it's cooked to a safe amount. Now, let's go ahead and talk about and review thermal energy and temperature. We know that thermal energy is the total kinetic motion, energy of those particles, right? We know that. Now, temperature is the average kinetic energy, that average kinetic energy of those particles. So when we take a temperature of something, it's going to be the average, making sure that, again, our food is safe. If we take the temperature of our head, that's just going to be the average energy of the kinetic, of those kinetic energy of particles moving by our head, the heat that is coming off of it. Now, heat is the transfer of energy, okay? Heat is the transfer of energy. So if you have more heat, you have more transfer of energy. Remember, the energy is conserved, but it can still be converted to different forms and or transferred. Okay, it is conserved, but it's still being converted to different forms. Again, when we talk about heat and we talk about that light bulb, this is a perfect example of heat transfer. Let me go back here. We have an electric energy coming in, and what's being radiated is heat. Okay, so it is just being transferred, and then from there, it's just being absorbed into the atmosphere or being absorbed into the surrounding area. Okay. So that's just kind of a review as we look at that. Now, let's take a look at temperature in phase change. Okay, and this is what's important. This is, if you haven't taken a look at that video from yesterday, this is where it comes in. But if you haven't, it's okay, you're still good. Now, during a phase change, when there are two phases, temperature does not increase. What do I mean by two phases? When you have both a solid and a liquid or a liquid and a gas that coexist, then the temperature does not change. It will always be 0 degrees Celsius right here at a melting point, or when you're at heat of vaporization, it's going to be 100 degrees Celsius, boiling point of degrees Celsius. Now, only once a substance is in a single phase, when I have a single phase, I'm either in a solid, liquid, or a gas, okay? That's when the thermal energy starts to increase the speed of the particles. In essence, it increases the temperature, okay? So only in a single phase, that's when you have an increase in temperature causing an increase of speed of particles. When you have those two coexisting, no temperature change, there is no temperature change, and it is at 0 degrees Celsius or 100 degrees Celsius. Heat of fusion is colder than heat of vaporization. Okay, just kind of be aware of that. These are the answers to numbers 5 and 6. I'm going to give everybody 30 seconds to go ahead and lock those in. Go, go, go. Alrighty, so let's go ahead and just check in. Again, remember number 5 and number 6, separate and temperature. I know these are kind of big words. Make sure that you spell them correctly. That does count. So still looking here, Mario, JJ, Jacob, Evie, Colin, Aramis, and Alan. Let me know how you're doing. Raise your hands when you're finished. Good, Evie. Nice job. Colin. Thank you, JJ. Awesome. Mario, Jacob, and Colin. Mario, Jacob, and Colin. Go ahead and raise your hands. Perfect. All right, let's go ahead and move on because I don't want to waste any more time because of our time constraints. All right, so let's go ahead and go back to that food thermometer. Now, we use a food thermometer to measure the temperature of our food and ensure it's cooked safely. But what if your thermometer is wrong? Now, when you calibrate your thermometer, you won't calibrate your digital one. The reason being is that it's already digitally calibrated. So again, if you have anything, you probably press a couple of buttons and it calibrates on its own. Okay, and then you just change the batteries and so on and so forth. But if you have one of these thermometers, you can actually calibrate it. And the reason and how you calibrate it is that you can calibrate it by using ice water. Since the melting point, the solid and to a liquid, is always at 0 degrees Celsius, the temperature does not change. So if I go ahead and I calibrate my thermometer in ice water, I'm going to try to get 0 degrees Celsius because again, during that phase change between a solid and a liquid, there is no change in temperature. It's going to be 0 degrees Celsius. Now you can do it on the other end there. You can also calibrate your thermometer. What is always the temperature of water when it boils? Well, it's going to be 100 degrees Celsius. We just talked about that. And so between a liquid and a gas, you can go ahead and put your thermometer in boiling hot water and it will read 100 degrees Celsius to calibrate your thermometer. Obviously, you're probably not going to do that because you don't want to burn your hands, so you probably will calibrate your thermometer doing ice water. If you have one of these at your home, try it out. Do a little experiment, see if it does calibrate to 0 degrees Celsius. Now, what's interesting is that when you do look at this thermometer, mine starts beginning at about 50 degrees Celsius because you don't want anything 0 degrees Celsius. But again, that's how you would calibrate it, by just sticking it into ice water, and then you have now your thermometer calibrated. Just kind of a little hint on how thermometers work, and the reason why we can calibrate them is because of those phase change points, because temperature does not raise. No, not yet. Yins, let me see. Did we do number 5? I think we did. Yeah, we did. So we can come back at the end of class, Yins. Just remind me, okay? All right. So just like I said here, again, when both the solid and liquid coexist, or when the liquid and the gas coexist, so when two phases coexist, then the temperature does not change. It's either always going to be 0 degrees Celsius or always 100 degrees Celsius. Remember, heat of fusion is solid to a liquid, so that's going to be 0 degrees Celsius. Think of heat of vaporization. Think of boiling water. That steam that kind of helps you out. Okay, and that's always going to be 100 degrees Celsius. When only a single phase exists, so when you have a solid, liquid, and gas, that's when you increase the temperature. That's when you increase the motion of those particles. Okay, only in a single phase. So let's take a look here at this single phase. I'm going to only give all of you just about a couple of seconds here to mark which one. Remember, phase change is that two states coexist. What happens to your temperature? Single phase, when one state exists, what happens to your temperature? And then heat of fusion, what is heat of fusion? Again, and heat of vaporization, think of boiling water, hint, hint. Go ahead and take your line tool. I'm only going to give you 10 seconds to go ahead and mark this up. Go, go, go. Let's get some lines up there. All right, I'm just going to, hopefully we don't go over in time. Go ahead and get some lines up on the board. I want to go over these lines really fast. Remember, phase change, two states coexist. Good, good. Now we're getting it. Good. When two states coexist, what happens to the temperature? Does it increase or not? Be careful with the phase change. Be careful. Phase change, does it increase temperature? I'm going to go ahead and put your whiteboard tools on hold there. Be careful with that phase change. So let's go ahead and take a look at number 7. Okay, we are getting a little caught up here with phase changes. Now remember, when two states coexist, temperature does not increase. That's why we can calibrate our thermometers here. So temperature does not increase. Energy is used to separate the particles, okay, but does not increase the temperature. Whereas in the single phase, that's when temperature increases, resulting in temperature increasing, the particles, or the motion of the particles, start to increase also, okay? Then heat of fusion, go ahead and lock your answers in. Once you lock your answers in, go ahead and raise your hand. Heat of fusion is when energy is needed to change from a solid to a liquid. Think of cold, okay, 0 degrees Celsius. And then heat of vaporization, I always think of boiling water from a liquid to a gas. Kind of helps me. If I know vaporization, then fusion is just right behind it. Okay, I'll know that one. All right, I'm going to give everybody about 25 seconds to finish locking in their answers. Finish locking in their answers, and then we're going to go ahead and go over endothermic and exothermic processes. All right, because of time, I'm not going to go ahead and check in with people, so just make sure that you have that. So let's go ahead and talk about endothermic reactions. Now, endothermic reactions, or endothermic, means heat enters into the reaction. Okay, heat is being absorbed. Now, I always like to look at this and kind of put this together. Is endo begins with the same letters as enter. Okay, endo, enter. Now, thermal energy is absorbed into the substance, and when thermal energy is being absorbed into the substance, obviously it's going to increase that temperature. It's going to increase those particle motions, and you're going to have more kinetic energy, resulting in melting, evaporation, and sublimation. Okay, sublimation is really kind of one of those hard ones. Take a look at the recording from tomorrow or from yesterday, and you'll understand. Okay. So melting, evaporation, and again, it goes this way. Energy is entering in. Heat energy is entering in, obviously increasing the temperature, causing the ice to melt. The melting ice is then going into water or liquid. And then from there, as more heat energy enters in, it then gets evaporated into water vapor or a gas. Okay. Now, on the other hand, you have something called exothermic. Now, exothermic is where the heat exits. And I'm going to go ahead and put A right here, exits. And if you look at the beginning of exo, begins with the same letters as exit, EX. So here is where the thermal energy is released from the substance, decreasing that temperature and decreasing that particle motion. So freezing, condensation, and deposition. Okay, so let's go ahead and take a look at this in this chart here. If I have energy coming in and that heat energy is being released from our water vapor, obviously we're condensing. We're going to have those, think of that cold Coke can that has those water particles now on the Coke can. Okay. Then from there, we have the water that is going to release that energy again, release that heat. And when I release that heat, I'm freezing into now an ice cube. Okay, I'm freezing now into an ice cube. So that's just kind of how you think about it. When exothermic is the energy releasing, things get colder. Energy, or exothermic, exit, heat exits. All right. Artemis, we'll go back. All right. All right. So from this, let's go ahead and submit our notes. We defined and applied conservation of matter and energy. We defined thermal energy, heat of fusion, and heat of vaporization. We talked about how thermal energy affects particles in a single state, comparatively speaking, when we talk about a phase change. And then we talked about endothermic and exothermic reactions. So at this point, go ahead and submit your 1F notes. Hopefully you did well. We will have any questions. Tomorrow is going to be a project day, so make sure you work on your project. Get that in. That is due tomorrow. Anybody else? We will see you back here on Friday. Have a great day, everybody. We'll see you soon. Bye. And then I will go back to 5 and 4. 4 and 5. All right.